Hello, welcome back. So today we're going to talk about vectors. Okay, so a vector is a directed line segment. So if you have your axes here, it's a uh, it's a line segment that looks something like that. So it's not like a line that goes on, you know, to infinity in both directions. It has a starting point, and has an ending point, and has a finite length. That's why it's a line segment. Okay, so a vector usually the way you would see a vector being written is it's some sort of variable with an arrow over it. Sometimes you'll also see it written as, in some books they use kind of like a bold letter. So if you see like a bold letter, that's also sometimes a notation a lot of books use for vectors, but that's not the one we're going to use. We're going to use this. So vectors have magnitude and direction. Okay, so the magnitude would be basically its value. So an example of a vector would be like a force. So it would be like uh, a 30-pound force, and it's directed downward, something like that. Okay, so for the vector itself, though, its magnitude is equal to the length. So the length of the vector represents its magnitude, and if you just want to show its length without its direction, the magnitude without direction, you put the vector inside these absolute value marks. So this is just kind of a notation for meaning just the magnitude of the vector. So this would be the length of the vector. Okay, and then we have the direction is the angle, and that's just the angle theta. And again, the way that we're going to do it is we're going to define this angle with respect to the positive x-axis. So the angles are positive counterclockwise from the positive x-axis. Okay. Uh, okay. So there's another thing about vectors, which is that you can shift a vector without changing either its magnitude or direction. So the vector doesn't really change if you shift it to different locations. So you can shift its starting point, and it should still have the same. It should still be the same vector, because you can keep that direction. So let's say we were to start instead at let's say this point right here. So it'd be the same exact length, and it would be the same angle from some horizontal line. That would be the same exact vector. Or let's say we wanted to start over here. Again, its orientation and its magnitude and its direction don't change by shifting it in other directions. And we're going to see that a little bit later. Okay? All right, so I want to give you some examples of vectors. So all right. So the ones that are probably the most well known are the position. That's the s vector, velocity, the v vector, and the acceleration. Okay. So the position is basically a distance and direction. So let's say that we had some ball, being thrown through the air, and let's say at some instant in time, let's say that's the highest point, so it travels some path. We want to have a vector for its position at that instant in time. So we would draw an arrow like this that goes from our origin to the location of the ball, and that would be our s vector, our position vector. Velocity is speed, is its value, and it also velocity also has direction. So if we look at our same ball here. So the location of this ball, let's say that it has a velocity at the highest point. It'll have a velocity that looks something like this. So let's say that's the velocity vector. That's its direction of motion at that instant of time. And then acceleration is the rate of change. Its magnitude is the rate of change of velocity. And also it has direction as well. So again, we have our ball. And if this is in the air and there's no air resistance or anything, then it has a downward acceleration, a downward acceleration due to gravity. All right, so that's kind of an example of 3 vectors that you might see. Other examples of vectors are forces, momentum, torque. So some non-vectors are things that basically have magnitude but don't have direction. Those are called scalars. But examples of non-vectors would be something like kinetic energy, which is the energy of motion, doesn't have direction. Temperature, obviously the temperature of an object doesn't have direction, but it has a quantity. Or volume, those are just some examples of non-vectors. Those would be called scalar quantities. All right, so I think the thing that is most tricky about vectors are the representations. So in fact, there are 2 representations of vectors, or at least 2 mathematical representations of vectors. There's also different graphical ones, but okay. So the first one is what we've just said, magnitude and direction. Okay, so example of magnitude and direction would be you have some vector, you tell me its length, and then you tell me the angle theta. And the second representation is what's called component form. And basically the idea behind component form is that you give, rather than the length and its direction, you just say how much you move left or right and then how much you move upward. So component form would be something like this. So you move some direction, Vx, and then you move some direction, Vy. And then if you connect the dots there, your vector is given by the combination of those two, from the tail of Vx to the tip of Vy. That would be your vector V. Okay, so you either give the direction, your direction, and then how far you go in that direction, or you give how much you move left or right and then up or down. And those are the 2 ways. And so what we're going to focus on is kind of going between these 2 different representations. So if I give you magnitude and direction, you should be able to give me component form. If I give you component form, you should be able to give you magnitude direction. So what I'm going to do here is I'm going to put in some numbers just to make things a bit more concrete. That's my furnace again. Hopefully that's not too disturbing. But you have some vector, let's say it has a length of 4 units, and then this would be 50 degrees. That same vector given in component form would be something like this, where it moves this way would be 2.6 units, and then it goes up 3.1 units, and then that would be how you reconstruct that same vector as its x and y components. All right, so what we're going to do, we're going to talk a little bit more about component form. All right, so let's say that we have some vector, and let's say that our vector is something like this, and to get here we have to move 4 units in this direction, and then we have to move 3 units down. All right, so that is our vector. And so in component form, there are a couple things with how direction works. And it's basically if you move in the positive x direction, that is to the right. Negative x direction is to the left. Positive y direction is up, and negative y direction is down. So that's generally when I draw these axes, I only draw arrows in the positive directions for x and y. So that's the positive direction of x, that's the negative direction of x, positive direction of y, negative direction of y. So when I look at this, what this tells me is that I move 4 to the right and I move 3 down. So x is positive 4, y is negative 3. That tells me how I should create this vector. So 4 to the right and 3 down. All right, so the negative basically tells me that I'm going down instead of up. All right, so the notation for how you would write a vector like this, let's call it vector v, would be something like this. So you would do 4, and then this is probably a new notation for a lot of you, but 4 I hat, and then plus negative 3 j hat. Okay? And so basically what the I and j hat are called unit vectors. And I hat just basically means the x direction. And j hat means the y direction. Okay? And these are called unit vectors. So basically what unit vectors have is they have direction, right? They tell us x or y direction. But they are called unit because they have a magnitude of 1. So basically this number, the coefficient in front of us, tells it the magnitude in that direction, but the unit vector just gives the direction only. All right. So you might be confused about this ij thing, and basically the idea is that x, y, z, which are the common coordinates used in three-dimensional space, are in order. X, y, and z are in consecutive order in the alphabet. I, j, and k are also in consecutive order in the alphabet. So it's just a different set of consecutive letters. Sometimes you'll also see this is written as x hat and y hat, which is a little bit more clear, but in many mathematical cases they use I hat and j hat. Okay? And so the way you would write the general form for this vector would be basically the Vx okay, and Vx is called the x component, which is how far you move left or right, and then Vy is called the y component. So if you're asked to find components, that's basically what you're asked to do, is find these coefficients in that x and y direction. All right, I'll just put a little sidebar here about alternate notations that you'll see. I think I mentioned before, sometimes you'll also see in books. And again, you sort of have to be flexible with how you do this. If you see this in the future, you may see x hat and y hat representing the x and y directions. Your book also uses another notation. Where vectors are shown to have this kind of angled bracket. And that's to distinguish it from the rounded bracket, which is representative of a point. So vectors don't represent points, they represent kind of line segments. So rather than this being like the end point, this would be how much you move left or right and how much you move up or down from any particular starting point. All right, so let's get to conversions. So what we want to do, and I think the first 4 homework problems are converting from magnitude and direction to component form. Okay, so let's say that we have some vector x and y, and it's something like this. It has a length 4 and it's at 50 degrees. Okay, so so basically the strategy is to create a right triangle by extending a vertical line from the tip to the x-axis. Okay, so there are other ways of drawing these triangles, but this is the best way in my opinion. So you have your vector like this, and you take the tip and you extend a line downward, and then the other side is you create a right triangle with the x-axis. All right. So sometimes also these components, it's good to draw arrows to show that you're going right and then upward to create that vector. So this side would be Vx, and this side would be Vy. All right. So label the sides Vx, Vy, and then use sine theta and cosine theta to find Vx and Vy. All right, so that's what we're going to do. So we have our triangle here. I'll draw it a little bit bigger. So we go right and up. We have Vx, Vy, 50 degrees. And there in our triangle, the magnitude is always going to be the hypotenuse, so that the magnitude is 4. So if we use SOHCAHTOA, we get that sine theta. Oh, actually, let me write this as sine 50 is equal to opposite over hypotenuse. So this would be Vy over 4. So what we're going to do is we're going to take both sides and multiply this by 4. And when you do this, the 4 cancels out here, and you can solve for Vy. So I'm going to move the Vy over here. So Vy equals 4 sine 50 degrees. So if all right, let me do the cosine first, and then I'll do that. So cosine of 50 degrees is equal to adjacent over hypotenuse. So the adjacent is Vx. The hypotenuse is 4. So again, I multiply both sides by 4. And I get Vx is equal to 4 cosine 50 degrees. So let's calculate both of these values. So 4 sine 50. I'm going to round that to 3.1. And then I have 4 cosine of 50. I round that to 2.6. Okay? So the way that we would end up writing this would be the vector v is equal to the x value, 2.6 I hat, plus the y value, which is Vy 3.1 j hat. Okay? And that would be this vector in component form. All right. Okay. So let me tell you about a complication to this, and which is the cases where theta is greater than 90. So that was a case where theta was in the first quadrant, the vector was in the first quadrant, but if it's in other quadrants, it gets a little bit more complicated. But there's something that we can carry on from that, which is basically what we found is that Vx was the magnitude of the vector times cosine of the angle, and Vy was the magnitude of the vector times sine of the angle. And it turns out that these are going to be in general true for other ones as well. So in the cases of theta greater than 90 degrees, an example of that would be something like this. So let's say that we have a vector that is magnitude of 10, so something like this, and it goes 140 degrees. So we're in the second quadrant. Let's also call this vector v. Okay. All right. So I'll tell you that even though this angle is greater than 90, these equations will still work. If you were to just use Vx is equal to the magnitude 10 times cosine of 140 degrees, and Vy equals 10 times the sine of 140 degrees, you'll get the correct answers, because that generally works. So let's see if we can calculate this. So we have 10 cosine 140. I get negative, I'm going to call this 7.7. And I get 10 sine 140. I get 6.4. Okay, so I got a negative sign for one of them. Let's see if that makes sense. So this says the negative sign means I have to move in the x direction negative 7.7. That means 7.7 left, and then I have to go 6.4 up, right? So that is consistent with these signs, with that vector. Going left and then upward makes sense. So this vector would be negative 7.7 I hat plus 6.4 j hat would be the way you would write that vector. Okay, so I'm going to tell you an alternate way, which for me is conceptually more meaningful, but it's a way you can get the same answer, which is I like being able to do the sine, cosine, tangent thing on these. So what I do is I draw my vector, and I have a value of 10, but I like to create my own right triangle. So I extend that vertical line downward to create my right triangle. And this angle right here, here I'll use a smaller pen so it actually shows up, is going to be 180 minus 140. Right? So this whole thing is 180, and then from here to here is 140. So this one has to be 180 minus 140, so this has to be a 40-degree angle right there. Okay? And this magnitude is still 10. And so I would calculate Vx and Vy. So Vx would just be 10 cosine 40. And then what I would do here is I would put a minus sign in by hand. So that equation is not going to give it to me, but I just realize, I look at this and I see that it goes left. And I know that left is negative. So for me, I have to put it in. It's possible that I could make a mistake or something like that, but I prefer being able to see the right triangle when I do this. And so you get the same answer as negative 7.7, but I like reconstructing that triangle. And in my opinion, again, if you're going to do this, if you're actually going to apply some of this stuff later on, you're in a much better position if you can kind of connect these things together by recreating this triangle. It's a good habit to get into, is basically creating this triangle, finding the components from a triangle. So I don't know, I don't have to recalculate this. It's going to be 6.4. All right, but again, the trick is I have to put in a minus sign by hand if I see it going left or downward, which is an extra complication. But I think sometimes, you know, the one that requires more work is actually a better one in the long run. So I prefer this, but just know that these equations are true. One other thing is that we're defining positive angles from here, but it's possible that in a different circumstance, they may not give you this angle from the x-axis. So this angle is only with respect to the positive x-axis. If they give you some other random angle, then you'd have to think a little bit more, which I think this gives you a lot more flexibility if you're able to do something like this. All right. So I'm going to give you two to try on your own. All right, so you try. All right. So this first one is a vector like this that has a magnitude 20 and the angle is 75 degrees from the x-axis. So let's call this V. So we want to find find the components and write in component form. Okay, so that's one. And then our second one, I should write X and Y. Is we're down here in the third quadrant. So let's say it's like this. Magnitude of 3. And this is 250 degrees. Okay, probably should have drawn that a little bit steeper, but let's call this vector U. Okay, so why don't you try those in right now? I'm going to take a drink, and then you can pause it, try it, and we'll get to it in a second. All right, so let's get started. So what I would do first is I would extend a line downward from the tip to create my right triangle. So my right triangle would look something like, here I'll use blue. My right triangle would look something like this. 20, and then there would be a line downward, and then with the x-axis, right? And I like putting vectors on these things, so this is it goes to the right, and then it goes upward, and this is a 75 degree angle. Okay, and what I have here is this is Vy, this is Vx. All right, so it goes Vx to the right, Vy upward, and we expect Vx to be positive because it goes to the right, and Vy to be positive because it goes to the left. All right, so Vx is going to be 20 cosine 75 degrees, and Vy is going to be 20 sine 75 degrees. And again, we derived that earlier, but you could use sine again. So sine of 75 is Vy over 20, multiply both sides by 20, and you'll get this. Cosine 75 is adjacent over hypotenuse, so Vx divided by 20, multiply 20, and you get this equation. All right. So if you want to practice your SOHCAHTOA, this would actually be a good opportunity for you to practice using SOHCAHTOA on this if you feel a little bit unclear about that. So let's calculate these sides. So 20 cosine 75, 5.2. It's green. And then 20 sine 75. I got 19.3. Okay, so then my vector V, here I'll do it in blue, would be 5.2 I hat plus 19.3 j hat. So that would be my vector. Okay, let's look at this other one. So again, what I do is I extend it from the tip to the x-axis. So in this case, I'm extending it upward. So my vector, I'll draw it over here. It goes like this, a length 3, and then it goes to the left, and it goes downward. This triangle in this case is would be 250 minus 180. So 250 minus 180. Because 180 is from here to the negative x-axis. It goes past there, so it's greater. So that would be 70 degrees. So in my triangle, I have 70 degrees right there. And then again, I have my Vx, and I have my Vy. Now I notice that Vx goes to the left and Vy goes downward. So here, when I do this calculation, I'm going to put in an extra minus sign for both of these actually. So Vx goes to the left, so I'm going to put a minus sign there. And I know that this is the adjacent side, so that's going to be hypotenuse cosine 70. Okay, and then my Vy, I notice it goes downward, so because I know it goes downward, I'm going to put a negative sign, and I get 3 sine 70 degrees. All right, so let's calculate those. So negative 3 cosine 70, and I get negative, I guess say 1.0, and I get negative 3 sine 70. I get negative 2.8. Oh, I'm sorry if you couldn't see that. Okay, so then my vector would be negative 1.0 I hat minus 2.8 j hat. Okay, so those would be my two vectors. Okay, so I'm going to show you the alternate way. So maybe the thing that you did on this one was something a little bit different. Maybe you didn't even draw the triangle. You could have also done, using the general equations, Vx is equal to 3 cosine of 250 degrees, and Vy is 3 sine of 250 degrees, and you would have gotten the same thing. So if you're just putting in this full angle, this angle greater than 90, not from a triangle, then you don't have to put in a minus sign in here. All right, so if you're going to do this, don't put in minus signs by hand because it's going to come automatically. So if you do this, 3 times cosine 250 negative 1.0, and then if you have 3 sine 250, again you get the negative 2.8. So it happens automatically if you just put in this angle greater than. It doesn't come from an angle, you just use that general equation. You may prefer this, and I think if you're just trying to get through the homework or whatever, this is the last math course you ever take, I'm not going to harangue you for that. But if you're thinking of doing this or actually applying this, I think the longer way has a better benefit in the long run. If you're going to take physics, if you're going to take calculus, whatever, I think a good habit to get into is not one where you're just using equations, but ones where you have a little bit more understanding, where you can connect your conceptual understanding to different topics. So connecting this to sine and cosine, to creating right triangles, I think you'll be better off getting in that habit. But you do what you want to do. All right, so we converted from magnitude direction to component form. Now we're going to do the opposite. So we're going to go from component form to magnitude and direction. All right, so I think this is like problems 5 through 8 of your homework. Is something like this. So we have a vector v. Let's say it's like 3 I hat plus 2 j hat. So the way you read this is 3 is positive 3 in the I hat direction. That means you move 3 to the right. And 2 in the j hat direction, which means you're moving 2 up. All right. And so basically the strategy for this is to draw a triangle. You may see that this is kind of a pattern. Okay. So the way I would draw it is I would always draw Vx first. So you always want one side to be along x-axis. That could be positive or negative x-axis, so you would move like this, and then you would move upward. And then you would connect this tail to that tip, and that would be your vector. Okay? So you have your magnitude V and your angle theta. And what you would use is you would use Pythagorean theorem for the magnitude. And then you would use tangent for the angle. Okay, so let me show you an alternate way of possibly drawing this triangle. So you might have drawn it something like this. Maybe you drew it like this. So you go 2 up and then 3. So if you look at this, you would say, okay, so V and then theta or something like that. But it turns out if you do it this way, this is not the way to suggest. So there are ways of doing this. There's ways of doing everything. But this is not the way I would suggest. And the reason is it's because it's hard to identify the correct theta. Remember, theta is always written with respect to the positive x-axis. So you always want your triangle to have an angle with respect to the positive x-axis if you can. But in general, the x-axis is kind of what you're looking for. Okay? All right, so always draw in the x. When you're drawing a triangle, draw the x component first and then put the y component at the end of that one. All right, so let's do this. So let me draw this triangle a lot bigger. So here I'll do color coordinating here. Our magnitude and our angle here. So let's do the magnitude first. So the magnitude is Pythagorean theorem. So we have, a squared plus b squared equals c squared. And this is our right triangle. So we have 3 squared plus 2 squared equals absolute value of v squared. So this is 9 plus 4 is 13. You square root both sides, and then you get absolute value of v equals square root of 13, which 3.6. So there's our magnitude. Now for the direction, we're going to use tangent. And tangent in this case is kind of a useful choice in here, just because you're always going to have, when you have component form, you're always going to have the opposite and adjacent sides. So tangent theta is opposite over adjacent. So tangent theta is equal to 2 over 3. Now, if you solve for this magnitude first, you could then use like cosine is 3 over the magnitude, or sine is 2 over the magnitude. You could also do that, but if you want to do it first, then it makes sense to do this. All right, so I have tangent theta equals 2/3. So I want to solve for theta. So what I have to do is I have to take the tan inverse of both sides. So tan inverse of the left-hand side, and then I should write this on a separate line. And then it's going to be tan inverse of 2/3. Okay. So I take the tan inverse of tan theta. Just gives you theta. Whatever is inside the tan function comes out by itself. You can think of the tan inverse and tan as canceling each other out. And then we get tan inverse of 2/3. And if I do tan inverse, so on my calculator here, it's a second button, tan, and I get the tan inverse of 2 divided by 3. I get 33.7 degrees. Okay, so that's my angle. And altogether, the way I would write the magnitude is I'd be 3.6 units long, and then the at symbol, 33.7 degrees. Okay, so that would be, given the component, this component equation, you create a triangle, Pythagorean theorem for the magnitude, tangent theta for the angle, and that's what you end up getting. All right, So again, another complication is what about negative components? Which basically is the same kind of complication we had before, which is what happens if it's in the second, third, or fourth quadrants. Well, when in those cases it's a little bit more complicated. So let's look at this one. So let's say we have V equal negative 2 I hat minus 4 j hat, and the way we interpret the negative 2 for the x direction means it's moving to the left. So this would be 2 to the left. And the negative 4 in the j hat direction means 4 down. And again, we're going to do the same thing. We're going to draw a right triangle. So I'm going to draw 2 to the left. I'm going to go 4 down. And there's my magnitude. There's my angle. So another way, again, I'll just kind of point out that I put this 2 so this angle is measured with respect to the x-axis. You're always better off doing it that way. A thing that you might do sometimes, you might see, is you could do it like this. You could go 4 down, and then you can go 2 to the left. And I would not suggest you do it this way. So there are ways you could do this. If you're more sophisticated, you could figure out how to get yourself out of that potential pitfall. But again, it makes finding the angle more difficult. So I would not suggest you do it that way. Always draw the x component first and draw the y component after the x component. All right. But again, it's the same basic idea if we use the magnitude here. Using Pythagorean theorem, the square root of 4 squared plus 2 squared is equal to 16 plus 4, the square root of 20. And so the magnitude is equal to square root of 20. .5. Okay, and then we want to find the angle. So our tangent is opposite over adjacent. So tan theta is equal to 4 divided by 2. So if I take the tan inverse of both sides, so I take tan inverse of this. So this side is equal to theta. This side is tan inverse of 4 divided by 2, or tan inverse of 2. Here, I'll just write it 4 over 2. You get 63.4 degrees. Okay, so when we look at this, though, when we actually look at this vector, it actually cannot be 63.4 degrees, right? So if we look at this, we know our vector goes something like this. And so we know our angle has to be this big angle. But what we've solved for is not that whole angle. We've solved only for this little portion right here, which is 63.4. Okay? Which is just inside this little portion right here. So in order to find the angle for this vector, what we have to do is we know it goes past 180, is we add 180 degrees to it. So I took that answer and added 180. If you don't know how to do the second answer thing, it actually saves you a lot of time having to rewrite these things. Oh. So the correct vector would be 4.5 units long at 243.4 degrees. Okay, so understand what you're calculating, right? So this angle right here is from the axis, so we had to add the extra 180 degrees to it in order to in order to actually get the actual angle. Okay? So that's something you have to watch out for. In general, in the other quadrants, I'll give you kind of a little sidebar here. So let's say that you are in the second quadrant. You probably would solve for theta for this angle, but the actual angle you want is this. So the angle you want, what you would do is you would take, you would do 180 degrees minus theta, because you want the angle from here to here, and you know the whole distance is 180, so you subtract that amount to get that little green bit right there. In the third quadrant, you do kind of what we just did. So in this case, again, this would be your theta, and you'd probably have a triangle that looks like this. But the actual angle you want is one that goes all the way like that. So then you would, in this case, you would add theta to 180. If you're in the fourth quadrant, then you're probably down here somewhere. You have your angle like that. You probably drew a triangle like this, and the angle you want is this one. And if that's the case, then you would do 360 minus theta. All right. So, so when you're in these other quadrants, you have to be a bit more careful, because generally the triangle that you're going to create is not really the angle that you're actually looking for. And again, the reason this is going to be the case, that you can't just do it in this calculation, is because tan inverse is limited so that it's a function. It has a restricted range, so it's never going to give you these kind of much larger angles. Okay, so you have to use some thinking. You know, like, I don't memorize these. I actually just look at the picture, and I know that 180 is the whole, you know, basically the opposite direction, negative x-axis. I know 360 is this one, so that's basically 360 is all the way around. So I just sort of figure these out on the fly. I don't memorize them, but you can memorize that if you like. All right, so I'm going to give you some to try on your own. And again, you try this and see how you do. So I'm going to give you this vector. V equals 5i hat plus 1 j hat. And 2 is 2i hat minus 7 j hat. And the idea is to find the magnitude and direction. Okay, so why don't you pause this and try that on your own. I'll take a drink. Again, I hope you guys are taking notes for these problems. I just realized I might have been... Oh, no, I think it's the same. All right, so let's do this one. So, yeah, this one is a much finer tip. So this is 5 to the right, and this is 1 up. Right, because they're both positive. Positive in the x is to the right, positive in y is up. So what I'm going to do is I'm going to draw a triangle. So again, I always draw the right-left part first. So that's 5. I go up 1. And that's my vector with a magnitude v and angle theta. So again, I'll use green and blue. So the magnitude, square root 5 squared plus 1 squared, which is the square root of 26. So the square root of 26 5.1. And then I'm going to use tan theta is opposite over adjacent, which is 5. So then I take the tan inverse of both sides, and I get theta equals tan inverse. Okay, so I didn't show the taking the tan inverse of both sides. One of the things I hope is happening for you guys is as you guys are going through this, you can sort of automate these processes. You kind of do them enough times, you sort of see where they're going. So you can sort of take steps off if you get very comfortable. If you're not comfortable, do the step. I think actually people do a lot of harm to their own learning by prematurely skipping steps. But the angle is 11.3 degrees. So this vector is 5.1 at 11.3 degrees. Actually, let's call this u, so we don't get them confused. Okay. All right, so that's the first one. This one has a negative sign in here. So when I look at this one, 2 is positive in the I-hat direction, so that means that we're moving 2 to the right. And 7 is negative in the j-hat direction, so that means we're moving 7 down. All right. The positive tells you, right or left. Positive right, negative left. Here, positive up, negative down. So again, I always like to draw the x part first, so that's what I'm going to do. So I'm going to go 2 to the right, and I'm going to move 7 down. So my vector is going to look something like this. Okay. All right, so then let's do the magnitude is the square root of 2 squared plus 7 squared. The square root of 4 plus 49, square root of 53. So the magnitude is equal to square root of 53. 7.3. I used the wrong color. All right, it doesn't matter. All right, and then let's find our angle. Tan theta is opposite, which is 7, over adjacent, which is 2. So theta is equal to tan inverse. I know I should show taking the tan inverse of both sides. I'm just kind of tired. You should do it. I'm a bit too tired to do it. I'll do it next time. So this is 74 degrees. Now, if I look at this, obviously that's not the right angle. So the angle I want, if I were to redraw this, I know my vector goes kind of right and downward, something like this. The angle I want is this angle. And the angle I've solved for is, here I'll use this one, is this angle right here, 74 degrees. So what I have to do is I take this angle and I'm going to subtract it from 360 degrees. And so my angle is, I could probably do this in my head, but 360 minus 74, 286. Okay, so my final vector, I guess I changed this to u, but I wrote everything else as v. Here, I'll make these all u's. So my vector u is equal to 7.3 at 286 degrees. Okay, so that would be the appropriate vector. All right, so you have to use some common sense. You have to understand what you're actually calculating and how it relates to how we define angles. Okay, so that should get you through the first 8 problems of the homework. There are 2 additional topics I want to get through kind of quickly. I added them because I think if you see this later on, it'd be good to at least have some familiarity. We're not going to spend a lot of time on it in this course. But the first topic, there are 2 additional topics. The first one is vector addition. So you can add vectors, just like you can add things like forces. So, let's say you have a ball. Obviously, there's a gravitational force acting on that, and let's say that it collides with a bird or something like that. There's a force from the bird on the ball, and so you have a force from gravity and a force from the bird, and those two forces add up to create a net force. So you would add those two forces together to figure out the net or total force acting on that bird, on that ball. All right. So vector addition. One of the things about vector addition is that it's easiest in component form. And so let's say we have two vectors, 3i hat plus 2j hat. And let's say vector u is 1i hat plus 5j hat. So basically the strategy for doing these is to add the x components. So the x components are basically vx plus ux. That's the 3 and the 1 in that case. And then you add the y components, which are the vy and the uy. All right. So you add the x and y components. So let's say that we have some vector w, which is equal to the sum of these two vectors, u and v. Then for the I hat components, you would add the 3 and the 1. And then for the j hat components, you would add the 2 and the 5. So you can only add x components to x components, and you can only add y components to y components. What you get is you get 4 I hat plus 7 j hat. My phone screen froze, so it's possible that this is not recording. I'll plug it in and see if that makes a difference.